Hello everybody, welcome back to this channel. Today we're going to talk about the two topics, the theorems in the circuits in the phasor domain. These two topics are probably the most difficult ones based on the at least the exam results. Somehow, if I put this problem in the exam, the people could get it right. Really, in the percentage of probably 30%. Really. 30% of the students in the past somehow could, almost 70% couldn't get it. One of the reasons probably is because today's topic are heavily relying on the topic we covered in the first few lectures. The lecture number 1, especially lecture number 2 and 3. The element constraint, connection constraints, the KCL, KVL, all this stuff. So keep that in mind. If you didn't build a solid foundation, or you have anything that not clear to you about the previous lecture, you really need to get that cleared out in order to understand the things we talk about today. Although once you know this concept, it's not difficult at all. Okay, so two topics. One is superposition, which is one of the fundamental theorems in the linear circuits. And the second one is the Thevenin and Norton equivalent circuits. Let's look at the first one. So the superposition is really useful if you try to figure out the circuit and you calculate by hand, right? Also smaller circuits. So you have the circuit has multiple sources. You're trying to figure out a particular voltage or current in the circuit around the certain element. So the way you do it is you each time you solve a partial solution by energizing only one source, right? So let's say if you have n number sources and you turn off all the n number minus one the sources, and then you only leave one, and you have one source, and you can use the parallel, series, all these things to figure the circuit out, right? And once you get all of them, you do this n times for all the sources, and then you get a partial solution. You sum them up, right? You superpose the solutions, you get the final. So that's the superposition. So one of the things is really getting students really seeming difficult is one is you couldn't really get this one. So you may have current sources and voltage sources. When you don't need those, you want to turn them off. The current source becomes open circuit, right? In 201, we learned that, let's see if you have V and I, the VI curve. Let's see, I have I here, I have V here. And the voltage source will be looking like something like this, right? So for constant voltage, the current could be anything. That's the voltage source. So let's see, the voltage source V0. So you have voltage source V0. That means the current could be anything, and the voltage is just a constant voltage. And if you compare with the short circuit, right? The short circuit, the voltage across the short circuit is just 0, right? And the current could be anything. So in that case, the line for this one, let's see, this is the, let's see, I'm not using the passive sign convention. Let's see, this is for the short. So this is the I, and this is the I, and this is the V. And in this case, the I for the short circuit is going to be somewhere here, right, on the horizontal axis. So the voltage is going to be constant. And that's the same as if the voltage source is 0. Right? If V0, you got the same. If V0 is 0, and you got the same line. So that's the reason for the short circuit, why the voltage source becomes the short circuit. In some sense, the short circuit is a special case of a voltage source. The special case, the basis of voltage is 0. Similarly, for the open circuit and the current source, if you make the current source become 0, that means no matter what voltage you apply to that, and there will be zero current, and that's an open circuit, right? So make sure you get these two correct, and then everything else looks like a little bit will become much easier. Let's look at the first the example here. I have a simple circuit. I have two sources, one current source and J2, and another one is voltage source, a 12 volts with zero phase angle. Some student asked in a comment in the previous lectures about why I keep this zero, and is this same as 12, just 12? Yes, it is the same as 12. I would like to keep this zero just to remind us we are working with the phasors, not a 12 volts, the DC constant as we did in the 201. So that's the reason I would like to keep this phase angle. But technically, numerically, of course, the 12 with phase angle 0 e to j 0, that's equal 12. You are absolutely correct. Okay, so in this case, I'm interested in to find the voltage across this 2 ohm resistor, right? So that's so everything is labeled in this circuit. Now I have this is the impedance, right? So I have a J3. This is impedance. Why this is not admittance? If it is admittance for inductance, that should be 1 over j omega L if for admittance, right? So normally so in that case I would have a negative j something rather than J3. So for capacitance, I have also impedance because this is the 1 over j omega c, and I would have a negative imaginary part. But in any case, this circuit already given in the phasor domain, so you don't need to transform from the sinusoidal to the phasor anymore. And I'm interested in finding the V sub x. So the way I do it is just as I said, I do only energize one source at a time. So the sequence doesn't really matter that much. So let's see, we first keep the voltage source on and we keep the current source off. And so the current source become open circuit. And it's after we turn off the current source. Originally we had a current source here, right? So the current source off here. This is the first thing you need to make sure you understand this. In the past, if the student made a mistake, they replaced the current source with a short circuit. So you started with the wrong circuit. Of course, you will get wrong result, right? And we discussed why the current source turned off becomes an open circuit, right? So keep that in mind. After we did this, and everything else would be fairly easy, right? So in this case, we can use the voltage division we just learned in the previous lecture. And in this case, I label this a partial solution and the V sub x1. So this is not a total solution because I only have one source engaged or energized. And in this case, V sub x1, I can use the voltage division. Pay attention to here is, do I have a negative sign in this circuit here? Let's see if I choose, if I walk clockwise direction, so this is voltage rise and this is voltage drop, right? If I walk a clockwise direction. So this is from minus to positive, and that's the voltage rise at 12 volts. And if I walk from the positive to negative, so this is the clockwise direction. So in this case, we don't need any negative sign, right? So I would have 2 ohm the resistor divided by the total impedance, which is 2 plus J3 minus J5, right? So in this case, I would have times the total voltage, which is 12. So I have 2 over 2 minus J2, right? And times 12. So I have, let's see if I get this correct. So in this case, I cancel at 1 minus j. Remember how we calculate by hand? If I divide by a complex number, actually I just did a appendix A part 5, I believe, the conjugate, right? So we can multiply by this by conjugate with the numerator. So in this case, I have 1 minus j left, and 1 on the numerator, the denominator, with conjugate of a denominator. So at the conjugate of 1 over minus j is 1 plus j. I multiply both the numerator and denominator by the same complex number. I'm not changing anything, times 12, right? So what would be on the numerator? Numerator become 1 plus j. On the denominator, what we have 1 square plus 1 square, which is 2, right? So this solution here is quite straightforward, 6 plus 6j, both. So that's the partial solution we already got. So there's a half problem solved. And if we can get another half, and then we can add them as a solution to get a total solution. And the second part, since we already had the voltage source engaged, solved, and then we try the second step is by having the current source on and turn off the voltage source. Remember, the voltage source become a short circuit. Once we turn them off, the original voltage source become a short circuit. I use a red line to indicate there was something there, right? That's what the voltage source. Now I have the current source here. So in this case, the way we can find Vx2 is there are different ways we can find Vx2, right? So let's see, we can find it in 2 different ways. Now, the difficulty level looks like kind of a high because you need the other sort of the knowledge of solving basic circuit to solve each of these partial solution, right? Let's see, I can do 2 different ways. So let's see, I can do, first way is I do the current division. So let's call this Ix. So if, let's say Vx2 would be equal Ix times the 2 ohm, right? Times the 2 ohm is the resistance, because Ix and the V sub 2x form a passive sign convention, right? If they do not follow the passive sign convention, you need a negative sign in front of the whole thing, right? In front of I sub x. So this video is a little bit long because I'm planning about 3 video clips for this lecture. And I'm going a little bit more detail because I did a survey with a student. Some students mentioned I should have more detailed explanation of the math involved. So I just don't want get some of the students lost. Okay. So in this case, I sub x, I can use the current division. The I sub x would be equal to, if you use the current division, and you should use, let me do this. So there are the current division, you should use the other impedance, right? So the other impedance would be minus J5 and plus the total impedance, which is minus J5 plus J3 plus 2. And times the total current, which is the J2. Okay, so this is the I sub x. Okay. Times 2. And let me explain what I mean by the current division. Let's see, if I have a total current, I have 2 impedances. Let's see, I have a Z1 and Z2. You're trying to find this current I2, let's see. So this is total I. So what I use here is I2 is equal Z sub 1 over Z sub 1 plus Z sub 2. And you may ask where this comes from, right? So this comes from the fact that based on based on our original discussion was I should use y sub 2 times I, the total current. We learned in the current division is that we should use this, so we should use y sub 2 over y sub 1 plus y sub 2 times the total current. If you multiply this out, I get I sub 2, 1 over z sub 2 plus 1 over z sub 1 plus 1 over z sub 2 times I. Now I multiply z1 and z2. On the numerator, I multiply z1 and z2. On the denominator, what I get? Well, I get on the numerator here, the z2 will be cancelled. Sorry, z1 and z2 will be cancelled. I'm left with z1, right? And so the z1 and z2, so in this case, first one is z2. Let me put z2 here, and the second one here, I got a z1 left. So this is where this comes from, okay? So that's where I'm using why this comes from here. So basically, the current division for the two element the case is the actual proportional to the other impedance. It's similar like if you're working with some two-person team, right? If you have another teammate, he's or she is not willing to work, and that means she or he has a high impedance, and then you need to shoulder all the work, right? So basically what you need to do, the amount is proportional to the impedance of his or hers. And that's kind of an analogy I use. But in any case, you can get a number. I'm not going to go through the algebraic numbers. You can calculate that should be 5 plus 5j. And since we find out all the partial solutions, and we can find v sub x1. V sub x is equal v sub x1 plus v sub x2. That's the total solution we are trying to find. That's 11 plus 11j volts. And I should put a unit here, also volts. And this is the one solution we can, one way we can use. Or another way we find v sub x2, we can also use, we can do the source transformation here, right? And in that case, we can change this to the voltage source and the in series with this impedance. And this voltage source would be minus J5 times J2. And in that case, I replace this circuit. I can do the voltage division again. So that be Vx2 would be equal to 2 over 2 plus J3 minus J5 times the total voltage, which is minus J5 times J2. If you examine this, exactly this equation the same as we had here, right? So I have 2 times this and this 2 times here. So this is really a conceptual different, but the result definitely will be identical for sure. Okay, very rarely the circuit can be solved by only one method. So let's look at another method of solving the same circuit without using the superposition, right? I could solve this circuit by using the source transformation. I first do the source transformation for these two. I pre-draw this so I save some time. And in this case, this source here will become the series and source voltage source in the impedance will become the parallel source of these, right? Parallel of the source and the impedance, the same impedance. And now I have these two in parallel now, right? I have these two current sources in parallel. I can add them up. So by the way, this IEQ should be equal to VSB, the voltage, which is 12, 0, phase angle divided by negative J5. That's the IEQ, and which is negative 2.4J, right? because we multiply j, and this is j squared, and j squared equal -1, and we have negative times negative, and that's positive 1. I have j. So 12 divided by 5 is 2.4, and then we have and now I can add these two together. So this is j. This is 2. So these two parallel current sources will become one parallel current source. Then I apply the voltage, the source transformation again here. That will become this one here. This VEQ would become that parallel current source, which is 2.4J plus the 2J2 and 2J, and times the impedance. The impedance is the negative J5, right? So I have this at 22, so I have 4.8, 4.4, yeah, 4.4 times 5. So J times negative J, that's equal to 1. So I have a 224 volts. So this, of course, is amps. And in this case, now I can solve the circuit by doing this, the voltage division. So 2 over 2 plus J3 plus minus J5 times 22. And this will give us the same solution we had. So you could do many different ways of solving the same circuit, but it all boils down to the basics, right? So if you don't understand basics, it looks like seemingly very difficult. So this video clip is a little bit long, but that's for the superposition, and I'll start another clip talk about the Norton and equivalent circuits.